Okay, now next step is to share screen. Okay, good morning, everyone. And just still we have a couple of minutes or a minute left, but let me just start. Yeah, I hope all of you can see the screen. Okay, so we had started our discussion on Markov chains, discrete time Markov chains. So we looked at certain generalities about stochastic process and also the definition of Markov chain and so on. And we had also seen that it is enough to specify the initial distribution and the transition probability matrix to sort of assume that the Markov chain is completely given to us, because all the other basic mathematical these things are left to measure theory. So, and the principle is that the governing principle behind that is from the enough, and also we had mentioned that the Markovian property will be sort of inherently assumed in the description. In some cases, might be possible to derive it. In some cases, it is considered from the, let's say, the people who had investigated, from the domain experts and so on. Such an assumption is quite reasonable under the circumstances of the problem. That is why the Markov property has become quite a useful property. So first we will look at a class of examples, some of whom which have in themselves becomes objects of extensive study. So with these remarks, let me. So the first example, it is rather trivial. It's a completely deterministic motion. So we had seen last class what is meant by a stochastic matrix, and also the transition probability matrix of a discrete time Markov chain is a stochastic matrix. So let P be a stochastic matrix such that each entry is either a 0 or a 1. And yes, the state space S may be a finite set or a denumerable set. So in such a case, this P could be a finite square matrix or a denumerable square matrix. And now we also note that in a stochastic matrix, the row sum, if you fix a row, that is fix an I, and sum over the j's, j varying over s, that should give you 1. And since we have this assumption that each entry is either a 0 or a 1, there will be exactly one entry in any row which will be 1 and the rest are 0. So let us denote that particular entry, which will depend on, yes?
Sir, I have a question. So in a stochastic matrix, can you say that every column sum is 1?
No. Then such a matrix is called a doubly stochastic matrix. Okay.
Okay. So basically in a doubly stochastic, both row sum and column sum are 1.
Shall we wait? Let us not talk about doubly stochastic matrix now. Okay.
Okay.
So
no, what I am saying was that the row sum equal.
Please, row sum equal to 1 means, see that the thing is, if the initial state is I, the Pij gives the probability of going to a state J. And our assumption, I mean, the inherent thing is that starting from I, at the next step, it has to go to one of the J's in S. The J can be equal to I also sometimes. Okay.
Okay,
so
okay.
That is why that row sum being equal to 1, sort of it reflects our thing.
Okay. Okay, no. What I am saying was that basically row sum equal to.
Please, row sum is equal to 1, column sum need not be equal to 1. Even in this example, you can see. You can get a lot of such examples yourselves. Even 2 by 2, you can consider that. For example, the in the top row, first element, let us say, is 1. The bottom row, second element is 1. And the column, but the second column is completely 0. That also will be a stochastic matrix.
Okay.
So, see, when our focus is on something, no, I would like that to, later on you can ask your questions. But first, let us see what is required here. So, for each I in S, there is exactly one J denoted by HI, such that PIHI equal to 1 and PIJ equal to 0 for all J, which are, except that H of I. For example, for the first row, it could be the third element, P13 could be 1. In the second row, it could be the 100th element, which could be 1, like that. So now it is easy to see, given that description of Markov chain and what is the role of stochastic matrix or the transition probability matrix. If you start from I, in the very next step, you will go to H of I. So then at the time 1, you are at H of I, and the second time point, you will go to H of I, and things like that. So that's what I have stated here. This means that if the initial state is I, then x1 is H of I, x2 is H of I, and so on. And since this kind of a thing will become quite cumbersome to keep on writing, we have a kind of a shorthand notation. We write H super 2I is H of I, and H3I is H of H2I, which is like this. So in other words, if x0, the initial point is I, at xn, the process is at H super n I, with, that is the probability of this xn being equal to this state is 1. And you can also easily see that the function H on S need not be 1, 1 or on 2. For example, it can even be such that the H maps all the I to one particular point, J0. So this is a kind of trivial example, so that this kind of a thing is not really ruled out. Note it down if you want to. Of course, in such a situation, there is not much role for probability, right? There is practically nothing is random. The motion is not really random. It is sort of deterministic. All right, next slide, which we come to one of the most important examples in the subject. This is the unrestricted one-dimensional simple random walk.
Sir, can you once again go to the previous slide?
Yeah, sure.
Okay, it's fine, sir, fine.
Okay. Unrestricted one-dimensional simple random walk. So let us say P is a number which is between 0 and 1. And now the state space is all integers, positive as well as negative. So this motion is very simple to describe. If initially the process is at state I, then let us say the sort of P denotes the probability of getting ahead in a toss of a coin. The coin, let us say, is a biased coin, or P can even be half. In that case, it is unbiased coin. So if from state I at time 1, I mean, the head appears, then the process goes to, let us say, 1 unit to the right. I am assuming that the Z is ordered in this fashion, left to right. So if supposing the initially it is at 10, if the thing head comes, it becomes 11 in the next step. Had it been tail, it would have gone to 9. So Pij, the stochastic matrix in this case is Pij is equal to P if J is equal to I plus 1 and equal to 1 minus P if J is equal to I minus 1. And it is 0 for any J which is different from I minus 1 or I plus 1. So in this case, the probability of x1 being at I plus 1 given x0 equal to I is P. And probability of x1 equal to I minus 1 given x0 equal to I is 1 minus P. And probability of x1 equal to J given x0 equal to I is 0 for every other J. So the process moves to one of its nearest neighboring states at each stage. The steps are assumed to be independent of each other. Please note it down if you want. So at any stage, the location depends only on the location in the immediately preceding step and on P. So let us denote by x sub n the location at the end of nth stage, n greater than or equal to 0.
Sir, it will be small p, right? It depends on capital P.
That is because capital P depends on small p. You are right, but
Okay. Fine, we'll do small p, yes.
yeah. Okay, so xn denotes the location at the end of nth stage. Now put xi n equal to xn minus xn minus 1 for all n greater than or equal to 1. And therefore, you can clearly see that x at n is x0 plus xi1 plus xi2 plus etc. to xi up to xi n for any n greater than or equal to 1. And this xn, see xn minus xn minus 1 can be either plus 1 or minus 1. So it takes the value plus 1 with probability little p, and xi n takes the value minus 1 with probability 1 minus. So we had assumed earlier that the steps are independent of each other. And therefore, the mathematical way of expressing that is that, so this represents the step at the nth stage. Xi1, Xi2, etc. are independent random variables. So these Xi's are IID Bernoulli type. See, Bernoulli random variable we have seen takes value 0 or 1. Here it is -1 or 1. With type random variables with parameter P. So in this case, many properties of Markov chain can be analyzed using Xi1, Xi2, Xin plus Xin. That is the partial sums of these IID random variables. Note it down if you want. So if P equal to half, then the process Xn is called the one-dimensional simple symmetric random walk. Simple random walk because at each stage it can go to only the neighboring state. The next, the state immediately to the left or immediately to the right. And symmetric because those probabilities are equal. The probability of at each step going to one step to the right is same thing as the probability of going one step to the left. Okay, now I want to go, yeah. We have mentioned that the process moves to one of its neighboring states at each stage. Okay. Supposing at a particular stage, let us say the process is at 10. Then after some time, let us say it is at -20. So from 10 to -20, it has come. And because of this property, you know that the process must have passed through all the intermediate steps. From 10, it must have at some stage come to 9, and from some 9, it at some stage must have come to 8, and so on. Of course, in between, it could have wandered around to the right of 10 and all that. So what it means is, if at a particular time point it is at one point, let us say 10, and at another time point, it is at -20. So in its travel from 10 to -20, it has not skipped any of the intermediate states. It has gone through all the intermediate states. And that also shows that to go from 10 to -20, it must have taken at least about 30 steps. Because without skipping the intermediate sites, it is not possible to go reach the other one in less than, let us say, 30 time units. So that's what I'm mentioning here. Observe that the simple random walk Xn does not skip states in its evolution. That is, if for two states I and j, I not equal to j, if xm equal to I and xn equal to j, m less than n, that is this time point is less than this time point, then it must have passed through all the states between I and j. I hope that is clear. It's pretty obvious. So in particular, to go from I to j, it will take at least mod j minus I steps. So this is a kind of discrete version of continuity, going to the nearest neighbor at each step. In other words, this random walk, this kind of object has been studied first by physicists. And the random walks had traditionally been kind of discrete approximations for certain continuous time stochastic process, namely Brownian motion. Unfortunately, the connection between random walk and Brownian motion, we will not be able to see in this course or even the next course. So I think I am told some physicists still call the Brownian motion process as a random walk. Of course, those things will be in 3 dimension and things like that. But still, this is 1 dimension. Even 1-dimensional models are studied, I think, in physics in many contexts. So the nearest, going to the nearest neighbor thing, it's a nice property. Okay, please note it down. All the things concerning the simple random walk, whatever you want to. So let me go to the next slide, next example. This is again a thing concerning simple random walk, but let us say with 2 reflecting barriers. So let C and D be fixed integers such that C is less than D. They may be positive, negative. Of course, C should be less than D. So let us say the motion has this property. Suppose the process performs a simple random walk in the region C plus 1, C plus 2, D minus 2, and D minus 1. That is, whatever is in the interior, I mean, interior doesn't really make this thing, but whatever is strictly between C and D, it is performing a simple random walk there. But when it reaches C, at the next step, it doesn't go to the left of C. Therefore, at the next step, the particle has to move to C plus 1 with probability 1. That is why sort of reflection. It is reflected back into the interior. And similarly, when it reaches D, it moves to D minus 1 with probability 1. So in this case, the state space S is a finite set, C, C plus 1, etc., D minus 1, D. Note it down. And also, what about the transitions? Let us say in the interior, that is C plus 1 to D minus 1, it is like the random walk. So Pij equal to P if J is I plus 1, provided this I is strictly between C and D. And similarly, Pij is 1 minus P if J happens to be I minus 1. Again, when I is strictly between C and D. That is, the initial point is strictly between C and D. But when the initial point is C, then it has to come at the next stage to C plus 1. So P sub C plus 1 is 1. And similarly here, P sub D minus 1 is 1. And Pij is 0 for every other ing. So the two extreme states, C and D, are called reflecting barriers or reflecting boundaries. This process also does not skip states in its evolution. Please note it down if you want. Okay, next. So now we consider the next example, simple random walk with two absorbing barriers. Again, in this case, the state space is finite, C plus 1, etc., D minus 1, D. And C is strictly less than D. These are integers, fixed integers. As before, the particle performs a simple random walk in the interior, namely on the set C plus 1, C plus 2, D minus 2 to D minus 1. On that thing, it behaves like a simple random walk. But on reaching C, if it happens to C, it never comes out of C. It stays there forever. And similarly, the case of D. On reaching D, it just stays there forever. So in this case, again, you can easily figure out the Pijs. When I is between C plus 1 and D minus 1, the Pij and that Pii plus 1, Pi minus 1, these are same as before. But if the initial state is C, then Pcc is equal to 1. Similarly, Pdd equal to 1. And Pij is equal to 0 otherwise. States C and D are called absorbing boundaries. So this process also does not skip states in its evolution. Note it down if you want. So let us go to the next example. Note it down if you want all these things. Okay. Now we will look at next example, unrestricted general random walk on Z. So the state space is once again the set of all integers. Now let capital Q be a probability measure on Z. That is, Q of any singleton I is greater than or equal to 0 for all I. And if you sum these Qi's over I varying over S, all the integers, it is equal to 1. Okay. Now let Xi1, Xi2, etc. be IID random variables taking values in Z. And let us say they have a common distribution, this Q. In other words, probability Xi equal to K is Q of the singleton set K for any K in Z and also any I running over 1, 2, etc. Now let Xi sub 0 be again a Z valued random variable independent of all these guys, Xi1, Xi2, etc. And of course, we assume that this Xi0 need not be distributed according to Q. Of course, these notations using Xi, etc., and in view of the kind of previous notation we have used, it immediately should alert you that the process, the random walk, is going to be defined in terms of these Xi's, and you may also be able to guess it. Okay. So suppose X0 is Xi0, and X1 is Xi0 plus Xi1, and X2 is Xi0 plus Xi1 plus Xi2, which can be written as.
Can I go to your previous slide for Lakshmi?
Sure. Yeah, please note it down.
Okay, done. Yeah.
Thanks. So X0 is Xi0, X1 is Xi0 plus Xi1, and X2 is Xi0 plus Xi1 plus Xi2. So that can also be written as X1 plus Xi2. And in general, Xn is Xi sub 0 plus Xi1, etc., up to Xn. So that is X sub 0 plus Xi1, etc., Xn, which can also be written as Xn minus 1 plus Xi. then this Xn is a Markov chain with the transition probabilities given by. So the Pij is equal to Q at J minus I, that singleton set. So that is that probability of transiting from I to J in one step, that probability is given by this Q at that difference. And the initial distribution mu is the distribution of this guy xi0, x0 equal to xi0. That need not be this Q. So the Markov chain can move from I to J in one step with the probability Q of the singleton J minus I. Of course, since the xi's are independent, the steps are independent of each other. So in this case, to go from I to J, the process can skip all the intermediate states. Please note it down. I'll go to the next slide, if you like. So in this case, this process can skip states.
Sir, can you go to the previous slide?
Sure.
So here, sir, mu is the initial distribution. So here mu is the distribution of xi0. So what is the role of mu here? I'm not getting.
This is the starting distribution. No, that's like in our the discussion on last class. We said that to completely describe, sometimes you need the initial distribution mu and the transition probability matrix. This mu is up to you to choose.
Okay.
I'm just wanting to point out that the mu need not be equal to Q. That's only
Okay. So basically mu may be different from Q.
Maybe or may not be. It can be completely independent.
Completely. Okay.
For example, mu can be a degenerate distribution at some point, 0 or 10,000 or something like that.
Okay. So this is because xi0 is independent of xi1, xi2, xi0.
Yeah, that is a this thing of random variable. That it's not that doesn't reflect on the distribution, right?
Okay. Okay, sir.
For example, you can, as we have seen, you can have independent random variables with the same distributions. All these IAs are examples. Same distribution only means that certain kind of experiments are conducted at the same kind of conditions. Independent means they are conducted at independently of each other. Okay. So this process can skip states. Yeah. That's pretty clear. And this is, I think we have called example 5, I think. Yeah, this 5 is a generalization of the example 2, that is the unrestricted simple random walk. So try to figure out for yourself what is the analog of Q in that example. The next example is also going to be a generalization of the simple random walk, but in a different aspect. Okay. And these things also have colorful names, birth-death chains. So we are going to consider 3 cases. I mean, A will correspond to unrestricted case, B would be something about the boundary, C would have something involved about the boundary. Okay. So the notation P sub I, Q sub I, R sub I will have the same meaning in all these cases, which will give, you will see the meaning to start with in A, case A. So this is the unrestricted birth-death chain.
So what does the cases ABC signify? ABC?
You will see these are three different cases. The
Okay.
different types of birth-death chains. Instead of
Okay.
calling by each by a different example number, I have just putting them together. I could have done the same thing with the random walk, but just for some change, you know. Okay. Variety, that's it. So for each I in Z, let PI, QI, and RI be numbers such that the PI and QI are strictly positive and RI can also be 0. So P sub I is strictly positive, Q sub I is strictly positive, R sub I is greater than or equal to 0. And also these together, they sum up to 1. So in the unrestricted birth-death chain, this transition matrix is defined as follows. If you have finished noting this down, I'll go to the next slide. Okay. Pij is little pi if j is equal to I plus 1 for every I. And similarly, Pij is q sub I if j is I minus 1 for every I. And Pij is equal to R of I if j is equal to I for every I. In other words, this process at in one step, either it moves to the next immediate state on the right, or the next immediate state on the left, or it can even stay put in the same state. In the case of our random walk, this Ri was 0. And of course, it is Pij is equal to 0 if the difference between j and I happens to be greater than or equal to 2. That's also clear because these three guys add up to 1. So what do you expect in this case? Something analogy with what we have studied or seen so far in this lecture. Something you should be immediately able to guess. Doesn't matter, you come up with a wrong guess also, it is fine. Take a chance.
Sir, can you repeat, like, what should we do? Okay.
No, I just want you to sort of anticipate what is going to come. That's it. See, sometimes when you can anticipate, you feel that you already have a mental picture, so you can. This guy also doesn't skip states, right? Because any transition to a state at a distance greater than or equal to 2 is not allowed in one step. And at each step, it can either go to one step to the right or left or stay put. So there is no one-step transition to a state at a distance greater than 1 at any time in a single step. So this process also does not skip states in its evolution. The previous example that we saw, that general random walk, we mentioned that it can skip states in one step. Remember that, right? It can skip states. It is the generalization of the random walk because each transition is governed by the same mechanism, Q. Whereas in this example, this property is preserved. It cannot skip. However, the transitions, one-step transition can depend on that state I where it is now. In the random walk, that was not the case. Pi was equal to P for all I, Qi was equal to 1 minus P for all I, and Ri was equal to 0 for all I. So in that respect, this is a generalization. Not skipping intermediate states, that property is preserved.
Sir, I have a question. So what happens if we make either one of Pi or Qi to be 0?
Then that also becomes a kind of absorbing state.
Okay,
I mean, that kind of a transition is disallowed.
Okay, so if basically if Pi equal to 0, then we cannot move to the right.
You cannot move to the right.
Okay. Similarly for Qi equal to 0.
If you are putting Pi equal to 0, let's say P10 equal to 0. Once it reaches 10, it cannot go to 11. Then depending on Qi, it may go to 9. And depending on Ri, it may stay at 10 itself. All right?
Okay.
So
sir, we can say that if Qi equal to 0, then the process must always move forward. It cannot go back.
Cannot go back. It can stay put.
Yeah, it can stay at the same state, but it cannot go back.
Yes, like that.
Similarly for Pi equal to 0. Okay.
Yeah. So if supposing some Pi is equal to 0, then it would be constrained to move only to the left of that. Right? Yeah.
Excuse me, sir.
Yeah.
So the only difference between simple random walk and this is Ri can be positive. Is that it?
Not that. This Pi and Qi can depend on I.
Oh, okay. Yes, sir.
Okay, please note it down if you want to.
So basically, in case of simple random walk, Pi, Qi, they are constants. They are independent of I.
Yeah, correct. You are absolutely right.
And Ri equal to 0.
Ri equal to 0.
Okay, fine.
Okay. So another sort of comment is that the transition probability may depend on the current state, that's the present state. Like this Pi is P and Q, this is depending on I, right? Pi, Qi. So the transition probability, it can depend on the current state. So clearly, the unrestricted simple random walk is an unrestricted birth-death chain. Okay, that is the. All right, next, birth-death chain with one boundary. So one of you asked the question, what happens if some Pi or Qi is 0? That's what is going to happen here. So let us say this kind of 0 is going to be a boundary. For I greater than or equal to 1, let Pi, Qi be as in that case A. Like here, for I equal to greater than or equal to 1. And also for I greater than or equal to 1, Pij is given as in A. So if I is greater than or equal to 1, Pij is given like this. So from on 1, 2, etc., it just behaves like the unrestricted birth death chain. And at 0, Qi is necessarily 0, right? I think some of your earlier questions actually answers why. Because in this case, the state space is restricted to be 0, 1, 2, etc. So if it is at 0, it cannot be allowed to go to the left, which means Q0 has to be 0. Which also necessitates that P0 plus R0 should be equal to 1. So if P0 happens to be 1, that is P0 meaning P0, the capital P0 sub 01. If that is equal to 1, then the state 0 is a reflecting boundary. That is, on reaching 0, it immediately pushed to 1, the next step. If R0 equal to 1, P00 equal to 1, then the state 0 is an absorbing boundary. If both P0 and R0 are strictly positive and they add up to 1, then the state is 0 is partially reflecting and partially absorbing.
So sir, I have a question. So if the state 0 is an absorbing boundary, then if the process reaches state 0 at some point of time, it will stay there forever.
Forever.
Forever, okay. But if it is partially reflecting and partially absorbing, then yeah.
Wait. Partially, see, the thing is, if it is a reflecting boundary, that kind of a thing is used to sort of model elastic collisions, I think. That is what called elastic or inelastic. I always get confused. That is, if it hits 0, it is immediately is pushed back. Okay.
Yeah, when it is elastic collision.
Yeah. If it is partially reflecting, partially absorbing, if it hits 0, then it might sort of stay there for some time. And then at some other point of time, it might get back into the interior. So that kind of a thing involves the other one, the inelastic collision.
Inelastic collision, inelastic, yeah.
Okay. So, and especially on the higher dimension, if the boundary happens to be, let's say, the whole motion is in 2 dimensions, the boundary will be a line. So if it is absorbing, once it hits that, it can perform some motion on the boundary itself without coming to the interior. So like that. So these things are useful to model such processes. But we will generally will be considered these things. We will concern ourselves to the purely reflecting and absorbing boundaries and some that kind of things which we study. Okay, the last, the comments 1, 2, and that thing also holds here. That is, it cannot skip states. And also the transition probabilities they depend on the current state. That is, these things are dependent on I. Note it down. So the last this thing is with buttress chain with two boundaries. So in this case, the state space is 0, 1, 2 up to capital N, where capital N is a fixed positive integer. So sort of in the interior, that is on 1, 2 up to n minus 1, the Pijs are given as in A. In the sort of example, the unrestricted case. So as before, in this case, Q0 is 0. That is, if it is at 0, it cannot go to the left. And similarly, P sub n, capital N, is also 0. So as we have seen in the earlier case, state 0 can be reflecting or absorbing or partially reflecting absorbing. Same is the case with state n. And in this case also, this process cannot skip states. And of course, the transition rates depend on the current state. I. Yeah. So that's all for today. Next class, we'll continue with some examples which are maybe more specific. They are fairly not as general as this. So I think it's already quite in time. Some of you who have next class may be getting late. So let me stop sharing. So I shall end the session and we will see again on today is Wednesday, right? Friday, yeah.
You haven't shared the previous classes slides, right?
I have already put it up on this thing. Everything has been, so far, whatever has been put up on the YouTube Studio.
Not YouTube, I'm referring to slides.
That's what YouTube, you will see these things. The notes I have already posted.
Slides on Moodle, yeah.
Slides, we don't, this thing on Moodle, because I think the CMI, this thing is very limited, though they had told me last year itself, you cannot put slides on Moodle, because that occupies a lot of space. Okay. So,
okay. But you have put the notes.
Notes are there, you don't really need the slides.
I see.
Yeah, those are small PDF files. Okay.
Yeah, whatever's there in the slides, it's there in the notes. So
Yes, something more might also be there. Okay.
So sir, I have a question.
Yeah.
So regarding birthday chain with two boundaries. So we know that both the boundaries can be either reflecting, absorbing, or partially reflecting, partially absorbing.
Okay.
So we can say that there are 9 types of possibilities because depending on.
Doesn't matter. I say that reflecting, absorbing are the extreme, the two extremes we study. Okay.
Okay.
See,
So what will you do in the next class?
next class, some more examples.
Some more examples. Okay.
So